Welcome to section 1.2, Initial Value Problems. Objective number 1, define an initial value problem. An initial value problem, or IVP, consists of a differential equation along with one or more initial conditions, which provide specific values for the solution or its derivatives at a particular point. These initial conditions help narrow down a specific solution from a set of possible solutions. So initial conditions are typically written as y of x sub 0 equals y sub 0, or y prime of x sub 0 equals y sub 1, and so on and so forth. So in this initial condition representation, the value of the solution y is given at a specific time x sub 0. The number of initial conditions required depends on the order of the differential equation. For example, a first-order differential equation requires one initial condition, while a second-order equation requires two. For a differential equation of order n, we need initial conditions for y sub 0, y sub n, and so on, so all of the initial conditions at a given point to help us find a unique solution if one exists. When combined with the differential equation, these initial conditions form the initial value problem. In contrast, if the conditions are given at more than one point, particularly for differential equations of order 2 or greater, it is referred to as a boundary value problem, or a BVP. BVPs can have no solution, one solution, or multiple solutions, unlike IVPs, which typically lead to a unique solution or a particular solution. So two fundamental questions arise when we are considering an initial value problem. 1, does a solution of the problem exist? And 2, if a solution exists, is it unique? In a formal differential equations course, one can generally expect that most differential equations will have solutions, and that solutions to initial value problems will likely be unique or particular. However, real-world situations are rarely this straightforward. It's important to determine beforehand whether a solution to an initial value problem actually exists, and if it does, whether it is the only solution. So since the next two chapters focus on first-order differential equations, the following theorem provides sufficient conditions to ensure the existence and uniqueness of a solution for a first-order initial value problem. The discussion of existence and uniqueness for second-order problems will be deferred until Chapter 4. Theorem 1.2.1, Existence of a Unique Solution, states, let R be a rectangular region in the xy plane defined by x between a and b and y, which is between c and d, that contains the points x sub 0, y sub 0 in its interior. If f of xy and the partial f over the partial y are continuous on R, then there exists some interval I where h is greater than 0, so x minus h for the x coordinate, and then x sub 0 plus h for the y coordinate, contained in a and b, and a unique function y of x defined on that set interval, that is a solution of the initial value problem. So you might have read this and been like, what exactly is this even talking about? So let's break it down. So it starts off by saying, let R be a rectangular region in the xy plane defined by x between a and b and y between c and d. So let's stop there. So we know an xy plane is going to be the coordinate system. So if we look at this image down here, okay, this is our visual to help us understand this theorem. We have our rectangular coordinate plane, two-dimensional. We have our y-axis and we have our x-axis. And we have are labels on our x and our y axis. So there is some x between A and B, and there's some y between C and D. Okay, so those are our boundaries. All right, the next part says that contains the point x sub 0, y sub 0. So this is going to be our initial condition. Okay, that is our initial condition. So there's a point within this boundary, within this region R, that has initial condition or a point x0, x sub 0, y sub 0 in its interior, and that's what's labeled here. Okay, all right. If f of xy and the partial of f over the partial y are continuous on R, that means we have a function and the partial of that function are continuous, meaning there is no discontinuity. Then there exists some interval, all right? And so there is some interval I sub 0 between A and B, okay? H here is greater than 0, so making sure that the value of H is greater than 0, so that's just the distance contained in A and B, and a unique function y of x defined on that interval. So now there is a function y of x that goes through that initial point that is on that said interval I. Okay, so our interval is the neighborhood in which x sub 0 exists. All right, and we know, so this is the neighborhood in which x sub 0 exists. So that's the interval. So then there's a solution of the initial, oh, and that is, sorry, I spoke incorrectly. That is a solution of the initial value problem, okay? And the initial value problem says that y prime equals dy dx, which is f of xy, such that y x sub 0 equals y sub 0. And that was given to us by our initial condition in the theorem. Okay, so the existence and uniqueness theorem states that a first order differential equation of the form dy dx, which is f of x of y, has a unique solution passing through the point x sub 0, y sub 0 if the function f of x, y is continuous in the region R that includes the point x sub 0, y sub 0, and 2, the partial derivative of partial f over the partial y is also continuous in that same region. That's all that this theorem states, but we're going to use this theorem to answer some example problems. All right, objective 2. So objective 2 says solve initial value problems. So we have two problems that we are, actually no, we have a couple of problems that we're going to solve, but for this one, for our first exercise, we are told that provided below is a one perimeter family of solutions of the first order differential equations, that's DE, y prime plus 2xy squared equals 0. We need to find a solution of the first order IVP, so the initial value problem, consisting of this differential equation and the given initial condition. So give the largest interval, I, over which the solution is defined. So we have our DE. Let me label that here. So this right here is our DE. Then we are given y equals 1 over x squared plus c, and this is the solution, the general solution. Then we have y of negative 2 equals 1/2, and this is our initial condition. Okay, where when x is negative 2, y is 1/2. So that gives us the point -2, 1/2. Okay. All right. And so now we can find our particular solution for this DE. So I'm going to go to the next slide to start that. All righty. Okay, so we know our general solution and we know our initial condition. Okay, so our initial condition was y -2 equals 1/2. Okay, and we know our general solution is y equals 1/x² plus c. Okay, so since we know that when x is -2, when x is -2, y is 1/2, we can substitute that into our general solution to find c. So let's do that. All right, so now we have y -2 equals -2² plus c. So y of -2 is 1/2. So then we have 1/4 plus c. Okay. So in order for these two ratios to be equivalent, 2 must equal 4 plus c. And so then c will equal -2. So now that I know that c equals -2, I can rewrite my general solution. So that would get me y equals 1/x² minus 2. Okay, and this now is my unique solution or my particular solution. Okay, all right. So now that I have my particular solution, okay, we can find the interval. That's what it is. We can find the interval over which this solution is defined. Okay, and so in order to find the interval in which this solution is defined, we need to, because it's a ratio, we can find out where it's not defined, and then we know it will exist everywhere else. So let's do that. Okay, so since this is a fraction, we know that when the denominator is 0, it is undefined. So if we set our denominator of our particular solution to 0, and we solve for x, we will then identify the x values that make our denominator 0. So we'll have x², if we bring the -2 to the other side, equals 2. Then we take the square root of both sides, and we'll get plus -√2. So that means our intervals will be from -∞ to -√2, and then -√2 to √2, and then √2 to infinity. Okay. All right, so these are the intervals where this particular solution exists. Okay, but we now have to consider which of these intervals contains our initial condition, because our initial condition is a part of the solution to our differential equation. So the interval that contains our initial condition will be this first one here. Okay, -∞ to -√2. All right, it contains the x value -2. So that means our particular solution to our DE that was given to us will exist on this specific interval of existence. Okay, so let's answer our question. So thus, y equals 1 over x squared plus 2 is a solution to y prime plus 2x y squared equals 0, such that y of -2 equals 1/2 and exists when x squared minus 2 does not equal 0. The interval of existence is two quickly there is negative infinity to negative square root 2. Okay, and that is our answer. Awesome. All right, our next exercise, we're asked to find a function whose second derivative is y double prime equals 12x minus 2 at each point xy on its graph, and y equals -x plus 5 is tangent to the graph at the point corresponding to x equals 1. So we're asked to find a function, all right, and we're given the second derivative of that function. And so to find the function, we're going to need to use the second derivative to find the first derivative, and then use the first derivative to find the function. So let's do that first. All right. So we know y double prime is going to equal 12x minus 2, sorry. So to find y prime, we will take the integral of 12x minus 2, right? So we'll integrate y double prime to find y prime, all right, of dx. And so y prime will equal 12 minus 1/2, not minus, oh boy, 12 times 1/2 x squared minus 2x, there we go, plus c1. All right, since we're going to have to integrate twice, we'll just use the subscript for our different constants. Constants, not consonants. This is an English class. All right, so to simplify this, we get y prime equals 6x squared minus 2x plus c subscript 1. All right, so now we're going to take that and we're going to take the integral to find our function y. Okay, and so y, when we take the integral, we'll get 6 times 1/3 x cubed minus 2 times 1/2 x squared plus c1x plus c2. So to simplify that, we will get 2x cubed minus x squared plus c1x plus c2. Okay, so now we have our function, but our function has two constants in it. And so we need to identify what values those constants represent to find our actual function f of xy. Okay, well, In addition to knowing the second derivative of our function, we know that there is a tangent to the graph at y equals negative y plus 5. Okay, so since we know that we have a tangent to the graph, we can find the point at which this tangent line is attached to our graph, as well as the slope of this tangent line, both of which will help us identify our constant C, our coefficient now, C1, and our constant C2. Okay, so we know, and let's just write this out, we know that y equals minus x plus 5. Okay, so we then know at the corresponding x coordinate, x equals 1, we can find the corresponding y coordinate, which would get us the point at which the tangent is attached to our graph. All right, so if I were to substitute in 1, I get negative 1 plus 5, which equals 4. So at the point 1, 4, the tangent line is connected to our graph, the graph of our function. Okay, now the derivative of this tangent line is going to be negative 1. Okay, so if we take the derivative of y, we get negative 1. So the derivative at the x coordinate 1 is going to be negative 1. Okay, and so this is our slope. Okay, so knowing this information, we can now find our coefficient C1 and our constant C2. Okay, so let's first apply the slope. So since we know y prime of 1 equals negative 1, we can use that to find our C1. So y prime equals 6x squared minus 2x plus C1. So y prime of 1, we will be substituting in 1 for x. So this would be negative 1 equals 6 minus 2 plus C1. So negative 1 equals 4 plus C1. So then C1 equals negative 5. Okay, so now we know that y prime is going to be 6x squared minus 2x minus 5. Okay, and we can enter in 5 into our function as well. And we're now going to use that function equation to help us find the constant C2. Okay, so y, you don't need any prime there actually. Y equals 6x squared, not 6x, it's 2. 2x cubed. Writing the wrong equation. 2x cubed, there we go, minus x squared plus minus 5. So that plus then now becomes a minus 5. Minus 5x plus C2. So now y1, so we're substituting in 1 We know y of 1 equals 4. So that would be 2 minus 1 minus 5 plus C2. So 4 equals negative 4 plus C2. So C2 equals 8. Okay. So knowing what C2 and C1 equal, we can now substitute them into our y function. So y equals 2x cubed minus x squared minus 5x plus 8. So that is the function whose second derivative y double prime equals 12x minus 2 at each point xy on its graph, and y equals negative x plus 5 is tangent to the graph at the point corresponding to x equals 1. Yay! We did it. All right, for our next exercise, we're asked to determine a region in the xy plane such that y prime minus y equals x has a unique solution whose graph passes through a point x sub 0, y sub 0 in the region. So we know that we have a region in the coordinate plane such that this differential equation, y prime minus y equals x, has a unique solution. Okay. Well, in order for it to have a unique solution that passes through a specific point, which means it has initial condition in the region, we need to first isolate our y prime, which is our f of xy. So to do that, y prime is going to equal y plus x. Okay, we know y prime according to our theorem. Y prime is f of xy. Okay, and if we were to take the partial derivative of partial of f over partial of y, so partial of f over partial of y, we would get 1. Okay, and both are continuous for all x and y in the xy plane. There is no discontinuity. Okay, so we have found our region, right? So this means that any point x sub 0, y sub 0 in the plane can serve as an initial condition for which the DE has a unique solution. All right. Okay, let's do the next one. All right, so in this exercise, we are asked to consider the initial value problem, y prime equals x minus 2y, with an initial condition y0 equals 1/2. Determine which of the two curves shown in the figure is the only plausible solution curve. Explain your reasoning. Okay, so we know right off the bat that we have an initial condition. So when x equals 0, y equals 1/2. So that gives us the point 0, 1/2. Okay. We also know that if we were to plug in this initial condition into our derivative, y prime equals x minus 2y, we would be able to find the slope of our curve. So y prime would equal 0 minus 2 times 1/2. So the slope at this point specifically. So y prime would equal -1. Okay, so We know that both of these 2 points, the blue and the red, both of these 2 lines, the blue and the red, both pass through the point 0, 1/2. We see that. Okay. But we also know that the solution curve must have a negative slope when x equals 0. So that means our blue line does not have a negative slope because it's increasing. And our red line has a negative slope at x equals 0, so it's decreasing. So that means the decreasing function at x equals 0 is the red line. And the red line would be our correct solution curve. Okay, so let me write that out for you. So the decreasing function at x equals 0, so the red line, is the correct solution curve. All right, that's it for this one. All right, that concludes the notes for section 1.2. Enjoy.